This is part 1 of lesson 9.2, Parametric Equations and Calculus. In lesson 1, we talked about a review of representing motion in parametric form. And now what we want to do is talk about how we can find some of the things like instantaneous rate of change of this particle, its maximum height. So things like when is it concave down, things of that nature. So we want to talk about parametric equations and how it's related to our calculus concepts. So we're going to start by talking about the derivative of a parametric curve. So a curve C is defined by the parametric equations x equals t squared and y equals t to the third minus 3t. So we want to find dx dt and dy dt for these. All right, so for part A, dx dt is going to equal, since x squared equals, x equals t squared, dx dt is going to equal 2t. And then dy dt, y equals, since it's up above there, we're going to reuse this. I'm writing it here, t cubed minus 3t. dy dt is going to equal 3t squared minus 3. But most of the time, remember, our parameter is time, and we're really talking about a function, y, that is in respect to x. So we want to know what is dy dt. So, I'm sorry, dy dx. So how we do that is we take dy dt and we divide it by dx dt. But the easier way to look at this is by looking at dy dt and multiplying it by dt dx. And I know technically this isn't really an algebraic relationship. You want to kind of think of it that way, so that if you were thinking this as algebraic quantities, this would simplify into dy dx. But technically that's not what we're doing. So what we're going to have is here, we're going to have 3t squared minus 3, which is dy dt, divided by our 2t, which is dx dt. And when we simplify that, if we can, sometimes you can, sometimes you can't. So this is going to stay just 3t squared minus 3 over 2t. So that is our dy dx. Okay, so now, how do you find the second derivative? So the second derivative, and this is something you guys are going to have to remember, these show up on the AP test, finding a second derivative. So to find the second derivative with respect to x, what you're going to do is take your first derivative with respect to t and then divide that by dx dt. So you have everything you need. You found dy dx, you have dx dt, and dy dx is a function of t, so we can take that derivative. So, but please remember, you guys are going to have to remember this. All right, so let's go ahead and do that for this problem. So we're going to take d dt of 3t squared minus 3 over 2t. And some of these can get a little cumbersome because you're doing fractions over fractions. So you just want to be real clear with your algebra here. So, because we're going to have to use the quotient rule for the numerator. So when we do that, we get 6t times 2t minus 3t squared minus 3 times 2. And that's going to be all over 2t squared. And then don't forget, we still have that all over the 2t. Okay, so the whole top part is the quotient rule here. This is our quotient rule. That goes with this. And then on the bottom, we have our 2t. So it's easy to like lose things along the way because you kind of have dx at the bottom twice on some of these fractions. So when we simplify this, we get 12t squared minus 6t squared plus 6, and this is all going to be over 8t to the third. So putting everything together, we get 6t squared plus 6 over 8t to the third, and we can factor out a 2 and cancel that out. So our second derivative becomes 3t squared plus 3 over 4t to the third. So there's our second derivative. Okay, so the next part of this question says, the curve C has two tangent lines at the point 3, 0, where the curve crosses itself. Find the equations. So now what we're looking at is where we have an xy pair that we can use to find our slope and then write our tangent line equations. So here's what we have. We have our xy pair is 3, 0, but all of our derivatives are in t, so we have to find the t that goes with that. So using the fact that x equals t squared, we can say that t is going to equal the square root of x, and so t is going to equal the square root of 3. If you notice, our problem says it has two tangent lines, so we need a separate slope here. So you want to be careful with parametric equations. You have to use both parts of the ordered pair to find all your t values. So we also have to use the idea that we have that y equals t to the third minus 3t, and so we have to set that equal to 0 and solve for t. And what we're going to see is we get three values here. We get t equals 0, and we get t equals plus or minus the square root of 3. So we did return the square root of 3, but now we have the negative value. Now we're going to discount this one, the t equals 0, because remember we have to be at the point 3, 0, and we won't get the 3 back if we put 0 in our x equation here. If we put 0 in for t, we're going to get x is 0, and that's a different tangency point. So now we have our t values, plus or minus 3, that we're going to use to write our equations. So now we can find our slopes and write our equations. So for t equal to square root of 3, we have our dy dx is from above, from part B, we have 3t squared minus 3 over 2t. So this is going to be 3 times 3 minus 3 over 2 times the square root of 3. So that is going to give us 6 over 2 root 3, which is going to give us 3 root 3 over 3, which is just square root of 3. So there's our one slope. And for t equal to negative the square root of 3, our dy dx is going to be 3 times negative the square root of 3 squared minus 3 over 2 times negative the square root of 3. So we are just going to end up with, we have the same kind of simplification except with a negative sign, so we get negative square root of 3. So now we can write our two tangent line equations. We have our xy, and now we have our slopes. So the one is going to be y equals the square root of 3 times x minus 3 plus 0, and the other one will be negative the square root of 3 times x minus 3. And so this is at t equals the square root of 3, and the other one is at t equals negative the square root of 3. All right. So now, here's a formal introduction of our derivatives. So we know dy dx is going to equal dy dt over dx dt, and we want to remember that our x derivative with respect to t cannot equal 0. And then we looked at the second order derivative, and that's this formula. And we can also do it again. If you notice, it's pretty much the same formula, that you're going to take the derivative of the second derivative and then divide that by dx dt. So if you notice, for all of our derivatives, if you're looking for an easy way to remember these, you're going to take the derivative of whatever equation starting with dy dt with respect to t, and then you're going to divide it by the dx dt. Every one of these you're dividing by the dx dt. All right, so now let's look at something where the parameter is theta, because we also have a lot of times when, especially with motion, we use sine and cosine. So given the parametric equations x equals 2 cosine theta and y equals 3 sine theta, write the rectangular form by eliminating a parameter. So this is a review of what we did in section 1 again. So I want to use the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. So I am going to square both of these. So I'm going to square x over 2 equals cosine x, or cosine theta. I got that from here. I divided both sides by 2. So I get x squared over 4 equals cosine squared theta. I'll do the same thing with the y. I'll divide both sides by 3. And I get y over 3 squared is going to equal sine squared theta. So I get y squared over 9 equals sine squared theta. So then I have that cosine squared theta plus sine squared theta equals 1, and that's going to be equal to x squared over 4 plus y squared over 9, and then we have an ellipse. So we're supposed to graph, and we get an ellipse just from the equation. So I can see that it's centered at 0, and I'm going 3 up and 3 down on the y, and 2 over left and right on the x. So it'll look like this. Okay, and then we're supposed to find the slope of the curve at theta equals 3. So we're going to find dx dt which is going to be negative 2 sine theta, and not dt, I'm sorry, I should write a theta here, dx d theta, and then dy d theta is going to equal 3 cosine theta. So my dy dx is going to equal my dy dt divided by my dx d theta. Sorry, I keep saying t. So this simplifies to negative 3 halves cotangent theta. And so evaluating that at theta equals pi over 3, we're going to have dy dx is going to equal negative 3 halves cotangent of pi over 3. So that's going to equal negative 3 halves times, let's see, 1 over the square root of 3. So rationalizing that, we're going to get negative 3 square root of 3 over 2 times 3. So that'll be negative square root of 3 over 2. All right, and then for part E, we are going to write the equation tangent line through this point, xy. So we need to know what the xy point is. So I can find x by taking 2 times cosine of pi over 3. So that's going to give me 2 times a half, which is 1. And the y is going to be 3 times the sine of pi over 3, which is going to give me 3 square root of 3 over 2. So now I can write my tangent line equation. So my slope is negative square root of 3 over 2 times x minus 1 plus 3 root 3 over 2. So I'm going to stop there, and I will finish the rest of this in the second part of the video.